Welcome to the Explainer. We've got a truly fascinating journey ahead of us today. We're going to explore the complete life cycle of composite materials. And I mean the entire life cycle, starting from the microscopic flaws that can pop up the very second they're manufactured, all the way to how we design them for the real world, and finally, how we handle them at the end of their life. For those of you following along with modern manufacturing curricula, our focus today revolves around what we call Course Learning Outcome 3, or CLO3. Basically, this represents a massive shift in how we approach engineering. It's all about recognizing the absolute vital importance of design for manufacturing and the inescapable necessity of composite material recycling. We're going to see how we build these advanced materials, how we can inadvertently break them during that process, and ultimately, how we have to take responsibility for breaking them down later.
Okay, let's dive right into this. Here's our roadmap for today. 1. The manufacturing defect problem. 2. What is DFM? 3. Designing for composites. 4. The end-of-life challenge. And finally, 5. How we recycle composites.
Starting us off, Section 1, the manufacturing defect problem. So we tend to think of robotic, automated manufacturing as flawless, right? Like a robot does it, so it must be perfect. Well, the high-stakes reality is that even the most highly automated composite manufacturing really isn't perfect. To fully grasp composites, we have to start our story way down at the microscopic level. You see, the aerospace and automotive industries have increasingly pivoted to thermoplastic composites because they offer just incredible manufacturing flexibility. They can be welded, they can be repaired, and they have incredibly high service temperatures. To build these massive structures, we use a process called automated fiber placement, or AFP. This basically uses robotic arms to lay down narrow tapes of material, consolidating them in a single step using heat and pressure. It's an absolutely amazing technology. But here's the catch. The inherent complexities of robotics, combined with all the multi-physical phenomena happening during that rapid in situ consolidation, can actually introduce hidden flaws. If the heat is just a tiny bit off, or the compaction isn't exactly right, microscopic defects get baked right into the material itself.
Now, what's really interesting about this slide, which shows a cross-section of a widely used commercial carbon fiber/PEEK composite tape, is what happens when things go wrong. Take a look at the specific areas marked with the yellow dashed boxes. You'll see what we call resin-rich pockets. These are dangerous little zones that completely lack any fiber reinforcement. And notice the upper surface marked by the orange dashed boundaries? Those are resin-rich layers. If these thick layers of pure plastic somehow get trapped between the plies of a composite, they create a serious weak zone. When a part like this takes a hit, experiences an impact, that area with no fiber reinforcement is incredibly susceptible to interlaminar failure, meaning the layers can literally split apart.
Let's break down these micro defects specifically found in these thermoplastic tapes. First up, we've got voids. Believe it or not, these tapes can come straight from the supplier with an initial void content ranging anywhere from 5 to 25%. Then there's surface roughness. Profilometry scans actually show an average morphological bump amplitude of 35 micrometers. Now, to put that into perspective, a human hair is about 70 micrometers thick. So relative to a tape that is only 150 micrometers thick to begin with, that is a massive bump. If those bumps aren't perfectly squeezed and flattened by the robotic roller, the incoming tape just won't make full contact with the substrate. And finally, as we just saw, we have fiber content variation. Those resin-rich pockets we talked about, they don't just cause splitting, they actually reduce the transverse stiffness and the failure strain of the entire composite. It is, quite frankly, a microscopic nightmare that engineers have to manage.
Moving right along to Section 2. What exactly is DFM?
So you're probably wondering, how do we prevent these microscopic manufacturing nightmares from completely ruining our products? Well, we have to stop blindly reacting to defects and instead embrace a proactive engineering philosophy. This is design for manufacturing, or a DFM, and it is exactly what it sounds like. It's the practice of designing a product while keeping the harsh realities of the manufacturing process at the very front of your mind, right from day one. It starts with a blank sheet of paper, figuring out what the product actually needs to do, and then integrating processing knowledge directly into the initial design. The goal is simple in theory, but incredibly tough to execute. You want to meet the end-use requirements with the lowest cost design, utilizing the best possible material and process combinations. Essentially, you're designing the part to squeeze the absolute maximum capability out of the factory floor.
Let's contrast let's call it the old way of engineering with this modern DFM approach. Back in the day, designers would often just create blueprints and essentially throw them over the wall to the manufacturing team, having zero clue about the capabilities of the machines that would actually make the part. This poor design methodology resulted in products that were way too heavy, had way too many individual parts, required super complex assembly operations, and ultimately led to terrible quality and skyrocketing costs. Conversely, a true DFM design relies on heuristics and best practices. It minimizes the number of parts, it builds multifunctionality into a single piece, it minimizes part variations, and it makes handling a breeze. So the crucial takeaway here is that effective engineering absolutely relies on anticipating exactly how a product will be processed and assembled before a single tool is ever cut.
All right, on to Section 3, Designing for Composites. Now that we've got a handle on the philosophy, let's look at how DFM applies specifically to composite materials. Because DFM isn't just a buzzword, it's a strategic roadmap. It acts as a tool guiding designers through 3 critical phases: concept generation, concept approval, and concept improvement. In today's hyper-competitive global marketplace, engineers have to come up with the best possible design in the absolute shortest amount of time, using the absolute minimal resources. So, by taking that knowledge of defects, the voids and resin pockets we were just talking about, and integrating it right into the concept generation phase, an engineer can adjust the geometry or the process selection immediately. You're basically eliminating processing problems before manufacturing even begins.
And I have to say, this is where composites truly outshine the competition. The real challenge in designing composite products isn't just crunching the engineering math. It's deeply, deeply understanding the processing and the material information together. Because composites are molded and formed from individual layers and resins, they offer the highest potential of utilizing DFM and part integration compared to traditional metals. Think about it. Instead of bolting or welding 10 heavy metal pieces together, a clever engineer can design a single, multifunctional composite structure that does the job of all 10. This drastically minimizes assembly operations and significantly drives down production expenses. It's a real game changer.
This holistic big-picture approach is exactly why this is a core academic requirement for modern manufacturing students. If you look at this syllabus excerpt for Course Learning Outcome 3, you can see the explicit goal is to instill an awareness of the importance of design for manufacturing, alongside the recycling of composite materials. This isn't just academic theory, it's the global standard. Today's engineers are explicitly taught that you simply cannot separate the design of a part from how it's made, and more importantly, as we'll see next, you cannot separate it from how it will eventually be disposed of.
Let's move to Section 4 and see how this builds the end-of-life challenge. Okay, so we've zoomed way in on micro defects, and we've hung out at the drafting table looking at DFM. Now let's zoom way out to the macroscopic environmental impact. What actually happens when a composite part reaches its end of life? For decades, we've been building these incredibly durable, high-performance parts. But that durability is kind of a double-edged sword when the product is no longer needed. Broadly speaking, the infrastructure for dealing with composite waste falls into 3 pretty stark categories. We can landfill or bury it, which obviously just takes up space and leaves plastic sitting in the earth for centuries. We can incinerate or burn it, which can release toxicity and completely waste the embedded material value. Or we can choose the third path, recycling. Managing composite waste has rapidly evolved from an afterthought into a massive, growing concern for both industry and government sectors alike. Which brings us to our final section, Section 5, How we Recycle Composites.
So to avoid filling our landfills with tons of aerospace and automotive waste, we have to engineer solutions for the end of life just as carefully as we engineered the initial manufacturing. And this brilliantly illustrates the 2 primary avenues the industry relies on to tackle this challenge. On one hand, we have regrinding. This is a mechanical process where the composite material is literally chopped and ground down into smaller flakes or powders, so it can be reused as a filler in new, lower-stress applications. On the other hand, we have pyrolysis. Now, this is a thermal recovery method. By subjecting the waste composite to extremely high temperatures in an oxygen-free environment, we can actually thermally decompose the plastic resin, essentially burning it away, while leaving the highly valuable carbon or glass fibers completely intact to be reclaimed. Both of these infrastructure methods have their pros and cons, but let's be real, both are absolute necessities if we want any shot at a sustainable future.
So you see, it all connects. It's like a giant puzzle. If you design a part with way too much material because you didn't account for automated manufacturing defects, you aren't just wasting money up front. You are literally creating more mass that must eventually be pyrolyzed or reground later. But by utilizing DFM, by integrating that processing knowledge into your initial concept, you make lighter, smarter parts. Ultimately, this leaves us with a critical, provocative question to consider. Will the next system you design end up as a permanent burden in a landfill somewhere,
Or will it be intentionally built with the complete manufacturing and recycling life cycle in mind? The decisions we make at the microscopic and design levels truly do have a massive, macroscopic impact on our world. Thanks so much for joining me on this explainer.